two identical solid spheres of mass m equals 1.8 kilograms and radius r equals 0.8 meters are connected by a massless rod of length L, which is 3.6 meters. Okay, the system can rotate about a pivot axis directed into the page located at L over 3 from the center of the left mass. The system is tilted relative to the horizontal by an angle theta, which is 20 degrees. Gravity acts down as shown in the figure. Okay, I don't think they actually showed gravity, but we'll assume gravity is like this. So force due to gravity, and then the rod is of length L, and this shows the rod extending this far. So I'm going to say that the rod actually extends within the solid sphere, like so. Because otherwise you'd have L being like 3.6 plus 0.8. You take into account the radius of the sphere, but I don't think that's what they're going for here, because they have L here and they have L there. So this whole length right here, 1/3 L plus 2/3 L, should be 1 full L. Oh, there's gravity. They did have gravity in. Good for them. Okay. What is the moment of inertia of the system about the axis of rotation? All right, so this is going to have to do with two concepts here. One, moment of inertia of a sphere, and the parallel axis theorem. So here, let's see here. I'm going to start by saying, all right, moment of inertia total will equal moment of inertia of sphere 1 plus moment of inertia of sphere 2. And we'll just say, I don't know, 1 and 2. Seems reasonable. I like it. And then we know that for each sphere here, we're going to have the moment of inertia will be 2/5 mr squared. But the parallel axis theorem, so the moment of inertia is something that's at a parallel axis, that's what the little two eyes are there, that's parallel lines. That'll be the moment of inertia of the center of mass plus m, I'm going to say d squared, where d is how far off set the axis is. So in this case, for sphere 1, that would be d. One way you can kind of see this work, like an example of this, is with a point charge, or a point mass. So if you have a point like so, you could consider it a very small sphere. And so the moment of inertia of this little point spinning around would be 1/2 mr, we'll call it a small disk, 1/2 mr squared. Well, if the r right here is 0, then the whole system is basically 0. But if we now have if we move it parallel axis theorem wise over here, we then have I equals 1/2 mr squared plus md squared. This part goes to 0 as we discussed earlier because this r is really small, basically 0. And we're just left with mr squared. And this right here is our equation that we're used to for a point mass rotating about a center here. So you can really kind of derive the equation for a rotating point, or which also works for a hollow cylinder, because it's a whole compilation of points, using the parallel axis theorem. And so intuitively, that's kind of important to understand. If you can understand that, then that gives you a good mnemonic for how to remember the parallel axis theorem. Because it's one of those things that's so simple that it's barely covered, and then you forget it. And by this time, you've already learned a whole bunch, and it's like, I don't want to learn anymore. I'll just skip one thing. And this really isn't the one thing you want to skip, because the cost-benefit analysis for studying it is positive. Cost-benefit. The benefit you get from studying it outweighs the cost of learning it. Okay, so we have 2/5 mr squared plus m, these are both m's of the sphere, plus d squared, which I'm just going to say as L over 3. L over 3 squared. Add this one over, it'll be 2/5 m, which is mass sphere, 2L over 3 quantity squared. We can then simplify this as, wait a second, did we, 2/5 mr squared plus, there we go. Terrible penmanship, terrible boardmanship, dark purple. So then we'll have 2/5 mr squared here, this one and that one. So we'll have 4/5 mr squared, where r is the radius of the sphere, plus, and then we'll have massless sphere, which I guess we'll be able to filter out soon enough, L squared over 9, plus, and then for this one, we have 2/3. Yep. We have m 4L squared over 9. This gives us, let's do m times quantity 4/5 r squared, which is interesting because it's all 0.8, plus, and this will be 1/9 plus 4/9 will be 5/9 L squared. And I don't think it's really worthwhile to try and combine those. So I have mass, which is 1.8. 1.8. This will be 0.8 times 0.8 squared, because I think the radius is 0.8, yep. Plus 5 divided by 9, which is probably like 0.55, and then L, which is 3.6, which will be squared. And we'll do that in the calculator. Up, on, clear. We'll start with the 3.6 part, because that's probably easiest. 3.6 squared times 5 divided by 9 plus 0.8, I'm just going to do cubed, times 1.8, and we get 13.88. 13.88. And I don't really know what the units are for that. I'm just going to leave them off for now. Kilograms meter squared. I'll put that on real quick. Kilograms meter squared. See if there's a possible answer here. I'm going to say it is B, 13.9, which is kind of like 13.88, just rounded to 3 decimal places. So that's not too bad. So the thought process here is, and I know it looks intimidating, is you write out, all right, the total moment of inertia will be the sum of the individual moments of inertia. You're like, well, why don't we have to worry about the rod? It's massless. I don't know what the formula is for a rod. They'll probably give it to you, but it's probably something of some sort of fraction times mass times r squared. Well, if this mass equals 0, then the whole thing will equal 0, and it's infinitely easy to spin. So the massless rod won't play a part because it's massless. So then I got 2 spheres. You'll be given, most likely, if not, then just memorize it for the test, that the moment of inertia for a sphere is 2/5. You probably know by now that the moment of inertia of a disk is 1/2 mr squared, which is the same as 2.5 over 5 mr squared. And it makes sense that a sphere is kind of like a cylinder, but a sphere has more of its mass towards the center, so it'll be easier to spin, which makes sense that 2/5, which is less than 2.5 mr squared. So basically it says that a sphere is a little bit easier to spin than a cylinder. And if you remember the 1/2 mr squared, the math says so as well. So that's one of the ways I'm kind of like, okay, that makes sense. So we have our 2/5 mr squared. We did our parallel axis theorem, which is just, you just add on mass times d over, mass d squared. In this case, d was L over 3, the distance that the axis was moved in a parallel fashion. And the other one was 2/3 squared. Okay, so that makes sense. Now I'm going to get rid of all this, most of this. Click. That's good. And I'll clean up this portion too. I don't want to. No, I'll leave it. I'm proud of it. Okay, this is a terrible grade. What is the direction of the torque due to gravity on the system about the axis of rotation at the instant it is shown? Okay, so first thing you do is you think, all right, torque equals R cross F. and it's specifically r cross f, where r is before the f. This is not the same as f cross r. So there is, there's a associative property, blah, blah, blah. You can't switch them. The order here is important. So what we're going to, the way you do cross products is, so first thing, cross product deals with sine of theta. And so we're going to draw out our forces and r's. So we have, whoop, whoop, there we go, force going down. And then we draw a radius starting at the axis of rotation, which is here, going this way. So this is r. Whoop. And another way you can think of this is the only part that's going to matter is going to be the perpendicular portion, because it's a cross product. You don't need to do it that way, but if you're having trouble with figuring it out, it's only the perpendicular portion that's going to matter. So the way you do cross products is you point in the direction of, do it this way, whoop, r, and then you bend your fingers in the direction of f. So in this way, kind of hard to do with the camera. So r cross f, whoop, like so, you're going to find out that your thumb points in the direction into the page. R cross f. Terrible. R cross f. So how do you do cross product? Point your fingers in the direction of the radius starting from the axis of rotation. Bend your fingers in the direction of the force, and your thumb will be pointing perpendicular. In this case, it's going to be into the page. So r cross f, and then we're going to have torque pointing into the page. So, it will be E into the, where's the direction of the torque? And really, you know that since it's a cross product, you're going to have two vectors that's going to create a third vector. The only time it doesn't create a third vector is if these two are parallel, in which case it's just 0, it doesn't matter. So the only two real answers you're possibly going to have are out of the page or into the page. 50-50 chance. But the way you do it, start from the axis of rotation, point your fingers, bend your fingers then in the direction of the force, and then your thumb will point in the resultant direction of the resultant vector. Right hand rule, so to speak. Okay, now next question then is, what is the magnitude of the torque due to gravity on the system? I'm going to assume this means this is net torque due to gravity on the system about the axis rotation at the instance shown. Okay, so we're going to have two competing torques. So one is going to be clockwise like this. The other one is going to be counterclockwise like so. And so we're going to have, I'm going to write this as torque clockwise minus torque counterclockwise. And we can kind of tell that the dominant one is going to be this one. I think I kind of assumed that. So this one I kind of assumed, whoop, net torque. And I just ignored the sphere on the left because this is going to have a bigger radius. Therefore, since they're both the same mass and they're both the same angle, the one with the greater radius is going to have more torque. But now we're going to figure it out using math and such. So moving down here, so we're going to have torque counterclockwise minus torque counterclockwise. And if I do this and somehow get a negative number, I'll just know that I chose the wrong direction for which one was dominant. So this is going to be R. I'm going to go again with the convention. This is 1. This is 2. So we have R1 cross force gravity 1. Whoop, and this will be cross product. So vector vector minus R2 time cross F force gravity due to 2. So this is sine of theta. In this case, theta is going to be the angle between the vectors. And we're going to be looking at this vector right here. So this is 20. This will be 90. 90 plus 20 is 110. 180 minus 110 gives us 70. So this angle right there will be 70 degrees. Your thought process might be like, well, why do we use this angle instead of that angle? And that's a good question. So if we look at from a mathematical point of view, we have one vector going this way and the other vector going this way. So we can look at it as, let's see here. That's 20 degrees. This is 90 degrees. The entire thing would be 110. And this is more trigonometry. On mode degrees. If we take the second quit sine of 110 and we take the sine of 70, they'll be equivalent. And so the angle between this is actually 110. And I just know from using the unit circle that sine of 70 is equivalent to sine of 110. Similar, if you look down here, we're going to have the exact same picture down here. So same idea. I should probably actually be using 110 degrees instead of 70, but it's the same. Okay, another way to conceptually understand that is you're going to have the most torque when things are perpendicular like this. So the closer since this is closer to perpendicular than to up and down, we're going to want a theta, sine of theta that's closer to 1 versus one that's closer to 0. That's just kind of an intuitive check to make sure that this kind of feels correct. So I know that's a little bit vague, but this really isn't. I don't want to dive too much into trigonometry here. Sines and cosines and such. Okay. Focus, focus, focus. So this one is, so we're going to have R1, which is 1/3 L, times sine of 70, actually 110, but it kind of sort of both works, minus 2/3, I think I have these backwards, it's okay, times 2/3 times L times, this time is mass times gravity, 2/3 L sine of 70, mass times gravity. Everything is exactly the same. I'm going to switch these signs right here, just so I work with a positive number. And then we have 2/3 minus 1/3, and we're going to have 1/3 L mass times gravity times sine of 70. So this will be then, let's see here. We know that L is 3.6, so we have 3.6 up here. It mentioned up there. Times mass, don't remember the mass, maybe 18. It's always 18. 1.8. 1.8 times gravity, 9.81. Probably could just use 9.8 or 10 times the sine of 70, which is like, we saw is like 0.93. And this should be the answer. So clear this, start from, make sure we're still in radians, or degrees, make sure we're still in degrees. So 1 divided by 3 times 3.6, make sure that gives us something good, 1.2 times 1.8 times 9.81 times sine of 70. 70? 70. So we have 19.912. 19.912. And this is going to be Newton meters because that's what torque is measured in. And we have 19.9. This one right here. And they go over the absolute value, so they don't care about the sign. The previous question was the sign. So what is the magnitude of the torque due to gravity on the system about the axis of rotation the instant it is shown? Newton meters, right? And 19.9. Okay, so that is how we figure that out. One of the key parts here is knowing that the torques of these will oppose each other instead of building on each other. Well, I guess they build on each other. One's negative, one's positive. You get the idea. They're in opposition. So that's how you approach this problem. It looks pretty difficult, but if you kind of break it down into each part, it's not too bad. Some of the key takeaways here are the idea of moments of inertia. You can just add up moments of inertia. You have your parallel axis theorem, also important. And you also need to know that torque equals R cross F. The order of R and F is important. You need to understand what cross products are. And from there, you can basically solve the problem. Not too bad. Hope that helped. See you next time.